Yeah.
Yeah. All right. I guess let's get started. Um, Most of you guys are here. So let me share my screen on my end here with you guys. Um, on the Moodle page here, I actually create these two links. So Zoom meeting links. So every time before the class begins, you can come to the Moodle page and click on this one, so you don't have to remember or look up in your email. Also, I put the office hour Zoom link here in case you want to ask me questions on one. You can click on that one. Okay. Um, So also, if you go down to where we start actually having the Zoom meetings, so I will, starting from this point on, I will add the YouTube link below the lecture link. Okay, so the previous tools are um, added here. So after today's lecture, I will add today's link. Okay, it takes about like 30 minutes after the class before I actually post it, because it takes a little bit time to upload the video onto YouTube. Okay, so that's what you guys can check on later. Yeah, just in case you didn't get something during the class, you can always revisit. Okay, so that's what we are going to do, or what I have been doing on Moodle, like posting stuff on Moodle. Okay, so that's on that. Also, just remind you guys, homework 7 is due in 2 days. Okay, it's due on Wednesday. All right, so make sure you work on the problems. And then in case if you have any questions, just go to the top of the page here on the Moodle, click on the second one here, it'll bring you to the Zoom meeting, um, and then I will get notification that you are waiting for me. Okay, so wait for a few minutes, I will join you in that way. Okay, so as I say, most of the time, we actually don't go out at all, so I should be available most of the time. Okay, unless it's late in the night, so then I typically put my cell phone into flight mode, so I wouldn't receive anything up to that point. Okay, so but that's what you can do over there. All right. So let me switch to the PowerPoint slides of the day. All right. So today we'll be looking at angular momentum, and then also moment of force, or we call torque, and then the principle of angular impulse and momentum. So all these quantities are actually analogs to the linear momentum, force, and then linear impulse and momentum. Okay, so it's kind of that way, but we are just talking about the in this case we are having object that is moving in a circular fashion or angular fashion. Okay, so um, so that's what we are going to do. You'll be able to determine angular momentum of the particle, and then apply principle of angular impulse and momentum, and then use conservation of angular momentum. Okay, so again, these are the few activities we'll be doing today. But again, we'll be doing the quiz first. Okay, the reading quiz first. So go ahead and then do the reading quiz, and then submit your answer via the chat feature here. Make sure you want to submit to me just privately. Okay, unless you want everyone to see your answer. All right, everybody sent your answers to me already? Okay, so we'll take a look here, all right? So the first one says, select the correct expression for the angular momentum of a particle about a point, okay? So if you read the textbook, it's going to tell you this is going to be equal to the R vector cross product of the momentum vector, okay? So the first one, the correct answer should be B, okay? R cross m multiplied by v. Okay, so that's the first one. The second one here. Now, if you're wondering what's the difference between B and D, so for vector multiplication, if you are doing cross product, okay, so R multiplied by one quantity, a vector quantity, okay, that's equal to something. In this case, it will be angular momentum. If you are doing the other way around, you are doing this quantity cross R, then it's negative of that one. Okay, so these two expressions mathematically may look the same to each other, but when you are doing vector multiplication, it will give you the negative of the other one. Okay, so B and D, they are not the same. Okay. On the second one here, it says the sum of the moments of all external forces acting on a particle is equal to. This would be referring to principle of angular impulse and angular momentum. Okay, so sum of moment of all external forces will be equal to the change, the time rate change of angular momentum. Okay, so it will be C. Okay, it's because the moment of all external forces multiplied by the time should be equal to the change of angular momentum. Okay, so it will be C here. So part the second one, the correct answer will be C. All right, so these are the answers for the reading quizzes. Okay, B and C. All right. Any questions you guys might have? Just unmute yourself and then talk to me. Okay, so I'll wait for a few minutes before we move on to the next one here. Okay. So we'll be covering 3 sections here, but they are just simple sections. Okay, so basically giving out definitions, and then most of the derivatives, if you feel that it doesn't have details, you can refer to the linear momentum sections earlier in the chapter. Okay, they are pretty much similar to each other one. So the first one here, it's about angular momentum. Okay, so the definition of angular momentum, here we use symbol h. Okay, so h, remember this is a vector quantity again. This is equal to, so we have h sub o. That's the where the object is rotating about. Okay, so this is the point where all the axes are rotation. So h sub o, that's where the notation is coming from. So h sub o equals to r, which is the position vector the object is, multiplied by cross multiply by the m times v, where m times v will be the momentum vector. Okay, so this is a 2 vector multiplication, and the result would be, if you do r cross mv, okay, you can do this as a matrix. So this is a 3 by 3 matrix. Okay, so what you do is you put ijk here, and then you put the components of the r's in the second line here. So then you have rx, ry, rz. Then you put components of the momentum over here on the third line here. So that's mvx, mvy, mvz. So that means the x component of the momentum, y component, and the z component of the momentum. Okay. So if you guys are doing this, I think for those of you guys took physics 1, we already talked about this one in physics 1, how to do vector multiplication when you have like 3-dimensional vectors. Okay. So if not, then you can refer to the links I posted over here. So cross product vector, you can click on this one. And in general, to find determinants of the 3x3 matrix. Okay. So this operation R cross MV will be you'll be doing actually determinant of this 3x3 matrix. Okay. So you can click on this one here. It will direct you to a YouTube video. Okay, so let's see. Let me see if I can share that to you guys. Actually, no, not this one. Right. So it directs you to the link where actually you are doing how to calculate determinant of a matrix. Okay, so starting from 2x2, and then you can scroll down to where it talks about how to calculate a determinant of 3x3 matrix. Okay, so briefly, this is what you are going to do. So if you have 3x3 matrix, in the case we have, if we are doing R vector cross MV, so then IJK goes here, Rx, Ry, Rz, and then MVX, MVY, MVZ goes there. Okay, so this is what you are going to do. You are going to take the first one in the matrix, right? Multiply by, then you kind of cover this line and cover this line. So A multiplied by the determinant of this 2x2 matrix. Okay, and then for 2x2 matrix, it's up in the page. So you can do that, you can check on that. So then basically this is what you are going to get. Okay, you're going to have A multiply E multiplied by I minus F times H. Okay, so this one. And then on the second one, you'll be doing minus. Okay, you take the second one from the top here and then cover this row and then also this column. Then you'll have this 2x2 matrix on this two. Okay, so doing that way, so that tells you how to do it. Okay, in that that one. Now let me show you the other one. The other videos. So this is the to a web page. Okay, and then these two are videos. Okay, so if you click on the video here, it will bring you on the PowerPoint. The first one gives you the direct you to the link. The next two ones direct you to these two videos. Okay, so this is how to do 3x3. Okay, you guys can review this later. All right. So I'm going to just pause this and go back to the PowerPoint slide. Okay. Going back to the PowerPoint slide. Yeah. All right. So you guys can check on those links. Okay. Or you can refer to your linear algebra textbook. I think that's all over there. Okay. Let's see. So no, I think we'll mostly just deal with 3x3 matrix here in the class. I don't think will be a more than 3x3. Okay, so that will be just it. Okay, so don't worry about that. All right. So I guess yeah, you can send me chat. I guess I can sometimes I do notice there's a chat coming in, but I think it's easier if you just unmute yourself and then talk to me. Okay, so then everyone also will hear the question. Okay, so the question I received was, will there ever be solving determinant of greater than 3 by 3 matrix? So the answer would be no. Okay, in this class. Okay. All right. Okay. All right, so that's on the definition of the moment, angular momentum. Okay, so now when we talk about linear momentum, we say if there's a force on the object, then the momentum of the object will be changed. Okay, similarly here, if there's a force on the object here in this case, then it depends. Okay, it depends because in this case we're talking about moment of the force, not just the force itself. Okay, so the moment of force is defined by the r cross so moment of force. I think we use m in this class. Okay, so yeah, there's multiple different notations people use across textbook. You can see in this class we use m is equal to r cross f. Okay, so then you'll be evaluating this quantity here. So there's r, there's also f. Okay, so both quantity you want to evaluate, not just force, external force. Okay, so if r is equal to 0, or if r is in the same direction of f, then moment of the force will become 0. Okay, so then in that case, angular momentum will not change. All right, so we'll be looking at both this guy, and then also the direction of these two. Okay, because for the magnitude of m, it's going to be rf sine theta. So so it's not only r, not only f, magnitudes of r and f, but it also depends on the angle the two makes. Okay, if the two makes angle of 0 degree, then it becomes 0. All right, so the whole moment becomes 0. All right. Okay, so this is what we have when we talk about linear momentum. Okay, so linear momentum, the change of linear momentum or time derivative. So this that means again time derivative of this guy is equal to the overall force, okay, on the object. Okay, so in this case, if the we are talking about angular momentum, then we'll be looking at angular moment of the force. So moment of force about the axis point O, that is equal to r cross f. Okay, so r cross f again, magnitude will be rf sine theta. So it depends on r and f and also theta. Okay, so if we sum up all the moment of the forces, all right, then that will give you the rate of change of the angular momentum. Okay, just like what we had for the linear momentum. So summation of all the forces is equal to time derivative of the linear momentum, or the rate of change of the linear momentum. So similar here. Okay, so we'll be looking at angular momentum time derivative of it, that should equal to the summation of all the moment of forces. All right. Assuming in this case we are looking for a system of multiple objects. Okay, so then you sum up that. Okay. Now again, in a system of multiple objects, so you probably have some internal forces, lowercase fi on each of the object I. You will have external forces on each of the object f, capital Fi. Okay. Now again, keep in mind, because all the internal forces they will sum up to 0, right? So then the moment, or this guy, the change will be just coming from the external forces, okay? The moment of the external forces, not the internal forces, right? All right. So then at the end, this is the equation you're going to have, okay? So summation of moment of initial moment of the forces is equal to, so you are doing this to each of the forces on each of the object, and then sum it all up, and then you're being just looking at the external forces here, all right? That should equal to time rate change. This means the dot means time derivative of the angular momentum, okay? So summing it all up, okay? So very similar to the linear momentum, all right? So then, let me see. All right, so this is basically the principle of angular impulse and momentum, okay? So this guy here, summation of the moment is equal to time derivative of this guy, or if you write in time derivative in that form, okay? So that means time derivative of it, okay? So now you move this guy to the left-hand side, all right? So then on the left-hand side over here, it becomes summation of moment of forces times dt, and then on the most right side here, it's just derivative of the moment of derivative of angular momentum h, okay? So then you'll be doing some integration to this side and then integration to this side. So this is what you have, okay? Or in this case, you can move this guy to the other side of the equation, you can rewrite the equation, so it becomes this guy, okay? So this equation looks very like the one we had earlier. So when we had, this is what we had earlier for the angular momentum. So we had L, okay, L1. That means the initial linear momentum plus summation of from T1 to T2, the external forces dt, okay? So I, that goes to L2, all right? So that was the linear principle of linear impulse and momentum, okay? And this guy is angular, okay? So this equation is principle of angular impulse and momentum, all right? So let's turn over here, the summation of integration of MO dt is called the angular impulse, okay? And then if in cases of 2D motion, it can be applied as a scalar quantity using the components about z. So that means you can break this guy into the x component and y component, okay? And then also this will be in x component, y component, this will be in x component, y component, okay? So you'll be just having the components form of this principle of angular impulse and momentum, all right? In the special cases of when the angular impulse acting on the particle is going to be 0, so that means summation when in this HO1 plus summation of T1 from T1 to T2 MI dt equals to HO, the final. So in the case of, let's see, anyway, in the case of this term will become 0, right? Oops. In the case of this term will become 0, okay, then you simply have HO1 equal to HO2, okay? So that means initial angular momentum is going to be equal to final angular momentum, okay? So then we have, if that happens, we have conservation of angular momentum, all right? So, so one of the example will be if a particle is only subject to a central force, okay? So as showing in the figure here. So the force, if that's the case, then the force is always pointing towards the origin O here, okay? So then R will be also in this direction, okay? So then the moment will be equal to R cross F. So the two are in the opposite direction. That means the angle theta will be equal to 190 or 180. So then sine of 180 becomes 0, okay? So if that's the case, then moment of the force is going to be 0, all right? So in the cases, if you have a satellite where the force is only central force, it's just the gravitational force between the satellite and the Earth, okay? So if you take Earth as the point O, then the force will be central force. So in that case, for the satellite, it's going to be having a 0 moment force, okay? So then its angular momentum should be conserved if you look at one point with respect to another point, okay? So if you compare the two, you should have HO1 equal to HO2, okay? All right. So let's take a look at the concept quizzes here, all right? So you guys can go ahead and then do the two questions here and then send me your answers with in the chat, okay? All right, I think most of you guys have given me your answers. So we can take a look here. It says, first one, it says, if a particle moves in the xy plane, its angular momentum vector is in. So if it moves in the xy plane, then it should be, the vector should be in the z direction. Okay, so this is, let me show you on my paper here. In the case of, if this is the x, or if this is x, this is y, this is z, okay? So x, y, and z direction. If there's a particle moving here with mv, and then this is the r vector, okay, r vector. So then its angular momentum, it should be equal to r cross m cross v, okay? Now, if you didn't learn the vector multiplication, you want to click the last link that we had I had previously when we introduced this out. Okay, so you want to take a look there. So basically, you are going to apply right hand rule here. Okay, so if this is R, this is V. If you are doing cross product, okay, so R, it's in the xy plane, MV, it's going to be also in the xy plane, okay? So then the cross product of two vectors, the resultant vector here, I should put the arrow like that. So the resultant vector will be perpendicular both this vector and that vector, okay? This is like, so you have z or k unit vector k should be equal to I cross j, right? X and y, and then that's z. So again, z is going to be perpendicular to both x and y. Okay, so in this case, if the object is moving in the xy plane, then the angular momentum has to be in the z direction. Okay, so it could be either positive z or negative z, but it's going to be in the z direction. All right, so that one is going to be C. On this one here, the second one here, it says if there are no external impulses acting on the object. So what happens to the linear momentum and also angular momentum? Okay, so from principle of linear impulse and momentum, we know that if there's no external forces or no external impulses acting on the object, then the linear momentum will be conserved. Okay, so that's for sure is right. But what happens to the angular momentum? All right, so let's see here. Okay, so I think for somehow the material I got from the textbook, it says this answer should be C, but I'm leaning to answer A because that's for sure. Now remember, or I don't know if you took physics one somewhere else. Remember, in physics one, if you look at the universal physics from OpenStack, okay, remember there's a case that if you have a hockey stick, right? So then if there's a force going in this way, if there's a force going in this way, all right, F1 and F2, okay? Now, if say F1 is equal to F2, right, magnitude wide, and then in this case, if the impact time, say, is very short time or period, delta t on F1 and then also delta t on F2, right? So if this is the case, the total external impulses on the hockey stick is going to be equal to 0, right? Because you will have F1 delta t plus F2 in vector form delta t. But these two are the same in magnitude. They are opposite in direction. Okay, I'm sorry. I'm indicating they are the same in magnitude. Okay, they should be in opposite in direction. So then the total impulse on a hockey stick in a data time t that the hockey stick receive will be 0, right? So if that's the case, then you can see if you give it impulse here and then there, if the two add up to be 0, okay, so then this hockey stick is going to rotate, okay, in this direction, right, clockwise, okay. So this is what happens if you have total impulse to the particle to be 0, okay. But I think the wording here is a little bit tricky. It says no external impulses, okay. So that kind, I think you can understand this in two ways, okay. So if it says no total internal impulses on a particle, okay, then the answer should be A, okay. But this case, it says that there are no external forces, okay, or no external impulses. So that's indicating this doesn't happen at all. So there's no force, no external forces on a hockey stick, then sure, the angular momentum should conserve, okay. So yeah, so for C, yeah, I feel like the little one is a little bit tricky. Okay, but if you say C, then I think it's correct. Okay, on this one. All right. Do you guys have questions on this one? Okay. All right. If not, then we will take a look at the attention quiz here. All right. This one says a ball is traveling on a smooth surface in a 3 feet radius circle with a speed of 6 feet per second if the attached cord is pulled down with a constant speed of 2 feet per second. Which of the following principles can be applied to solve for the velocity of the ball, where r equal to 2? I see most of you guys say B. Okay, that's correct because obviously we are talking about angular momentum today, so that should be the answer, right? So yeah, but actually that's not a reason. It's because if we look at this figure here, all right, if you look at what's the forces on the ball here, because you are pulling it down here, then the force will be the tension force, okay? So you can see this one is going around in the circular fashion, all right? So then this force, it goes through the center of the circle here. So then the force on the ball is a central force, okay? So when we said if there's only a central force on the object, then the moment or the angular momentum should be conserved, because the moment of the central force is equal to R cross F, okay? So R is going to be in this direction. That's R, this is F. They are making an angle of 180 degrees. So then if you look at the magnitude of this moment of force, it's going to be R times F times sine of 180 degree. Okay, so that goes to 0. Okay, so when you have moment of force goes to 0 on the object, then your angular momentum is conserved. Okay, so that's the reason here. So the correct answer on here will be B. Okay, so most of you guys got this one right. Okay, that's nice. All right. Now, the second one here says if a particle moves in the z and y plane, its angular momentum vector is in. All right, so I think I kind of did this one earlier, so let me just went through this with you guys, okay? So if it's in z and y plane, so that means the r vector is going to be in z and y plane, and then the momentum vector mv is going to be in the zy plane, okay? So the angular momentum vector should be perpendicular to both z and y, which means this is going to be in the x direction, okay? So on the second one, you should have A as your answer, okay? So that's why it's easy, so we'll just go into it like that, okay? So B and A on this two, all right? Now, let's take a look at the example here today, all right? So this one says if you have two identical spheres, both are 10 kilograms, of having 10 kilograms as the mass, or actually, yeah, two identical 10 kilogram spheres, so 10 kilograms as masses, and then there are forces on each of there's a force on each of them, 10 newtons a piece, okay? So 10 and 10 here acting at different directions. So, and then it says the rod is also subject to a couple moment, okay? M equals to AT, okay? A times T, this means time, okay? T in seconds, okay? Where T is in seconds, okay? So this guy, the rod also receive a moment. Sometimes it calls couple moment, so it still means the moment of force on the rod, okay? So it's still M, okay? So if you see couple moment, it just simply means moment of the force, okay? Now let's see what this one is asking for. This one is asking you to find the speed of the sphere at t equal to 4 if the system starts from rest, okay? So so there's this moment by the motor here to the rod, there's moment by this force P, there's moment of this force P, okay? So we can take a look here together. So you'll apply principle of conservation of energy and conservation of linear momentum here, okay? So we'll see here. So conservation of angular momentum says the initial angular momentum plus the angular impulse it receives should be equal to the final angular momentum, the summation of final angular momentum, because this one has two particles here, so we are having a system of two objects here, okay? So that's the conservation of angular momentum here. So on the first one here, initial angular momentum of the system, because you start from rest, so it's going to be 0, okay? Now plus for the total moment on the system, okay, so it comes from actually two parts, or actually from three parts. But the first one will be coming from this motors. So M equals to AT from the motors, okay, then you're simply doing integration from 0 to 4 second AT dt. That's coming from that guy. Now let's moment of force by this force P equal to 10. Let's moment of force by this force P equal to 10, okay? All this, if you look at the direction that the moments will make the system rotate, they are all going to make the system rotate in the counterclockwise direction, okay? So they are all in the same direction. And then I guess I forgot to mention, so for the moment of um, for the moments of forces, if they are making the system rotate in the counterclockwise, then we typically call that as a positive direction. And then if the moment is making the system go in the clockwise direction, then we typically say it's negative. Okay, so in this case, they all make the system rotate in the positive direction or counterclockwise direction. So this is positive, and then this 10 times 0.5. So R is 0.5, 10 is the force, okay? So we are just looking at the magnitude of it, and then you integrate from 0 to 4 seconds, okay? The fact that you have 2 here is because you have one force, P equal to 10 here, the second one here, okay? So then you multiply by 2. That's going to be equal to the final angular momentum. So final angular momentum, you have two objects, you multiply by 2 that are equal distance away from the point O here. So 2 times m times v, okay, and then times r. So h is equal to rmv. So this is the magnitude. Again, we're just looking at the magnitude here, okay. So then you solve on the left hand side, you add those two up to be 104. On the right hand side, you have 10 times v. Okay, 2 times 0.5 is 1, and then 1 times multiplied by 10 is 10, so 10v. So the final speed at t equal to 4 seconds then will be 10.4 meters per second. Okay, so again, you are applying conservation of angular momentum here to figure that out. Okay. And I guess when it says you're going to apply conservation of energy, I think we actually didn't apply that one here. Okay, so just forget about that. That it says you are going to apply conservation of energy. I think that's not the case here. I will change this later, but I didn't realize that it was there. Okay. All right. At the end here on the group problem solving, okay, so this one, it's very similar to the examples we just looked at, okay. So you have two balls here. So they are, again, 10 kilograms a piece. And then there's this rod that is having negligible weight. So a torque acts on the rod as shown as, so this is a moment, okay? So again, moment of force, or sometimes you see torque, okay? So again, you're getting different terminologies here, but moment of force or couple moment or torque, they are the same thing, okay? So they are just moment of forces, okay? Or whatever you call among these three. You can call them as moment, you can call them as torque, or you can call them, say, couple moments, okay? Either way, they are the same thing. So then this one tells you that this rod will give a moment or torque as t squared plus 2, okay? So it's asking you the speed of each ball after 3 seconds if each ball has a initial speed of 2 meters per second, okay, when t is equal to 0. So similarly, you'll follow the solutions in the example, but there's a couple of things are different. So the first one here, it's the two balls has initial velocity, okay, so then that means initial angular momentum will not be 0, right? Now also, you only got one torque by this rod rotating here. There's no forces on this one, there's no forces on that one, okay, so just one angular impulse you'll have by this, okay? I think we are close to running out of time, so I'll just post the solution later with this guy, with the PowerPoint, okay? So, and then pretty much that will be today's lecture. Any questions you guys have?
Yeah, Dr. Ho.
Yes.
So on the example problem, you so when you started to solve the problem, there's the 0 plus the integral from 0 to 4 8t. Why do we have the integral from 0 to 4 8t dt plus the integral from 0 to 4 of that other information? Isn't it just supposed to be of the moment, or am I missing something?
So actually, there are two forces in the system, one on each ball, okay? So that's the second integral there. So 2 times the mass times R, or 2 times the force, I'm sorry. Because force times R will be the moment, okay, of the forces. Okay, so that's the second integral. The first integral is given by the motor at the center of this rod that's rotating. So there's a motor at the center of the rod that gives you the moment of AT.
Okay, got you.
Okay.
All right, thanks.
Sure. All right. Other questions? So if not, then we'll stop here for today. Okay. So see you guys all on Wednesday. Bye.